How's it going, class? So we will continue with the Metabolism 2 lecture. We'll pick up from where we left off last time. We were wrapping up the phases of cellular respiration. Remember, overall, there are 4 different phases: glycolysis, transition, Krebs cycle, and the electron transport chain. Remember that the electron transport chain was the one that yielded the most ATPs, and it was happening specifically on that inner membrane of the mitochondria. And here's a little animation to recap what was happening in that electron transport chain. Remember, you have these electron carriers, and those electron carriers will accept hydrogens from NAD and FADH2. The electrons will run through the cytochromes, and as they go through the cytochromes, energy is released. Those are redox reaction processes, right, across the cytochromes. And that energy will be used to create a concentration gradient, basically a higher concentration of H plus in the inner membrane space. So water will be produced as the final electron acceptor. And now you have the concentration gradient for the H plus ions. They will go from a higher to a lower concentration, and that process will release energy. It goes through this specific protein called the ATP synthase, and ATP is produced at the highest numbers in that electron transport chain. That concentration gradient is actually really important, that you have a high concentration in that inner membrane space and a lower concentration in the matrix. There was a researcher, a couple decades ago, 3 decades ago, let's say, and what he did was he poked a hole in that inner membrane. The electrons were allowed to still shuttle across the cytochromes, but there was no longer a concentration gradient. So the redox reactions were still happening, but without a gradient, you're not going to make any ATP, because basically energy is not released through that ATP synthase. So it was a pretty ingenious experiment that he designed. All right, so this is happening in the mitochondria. Obviously, the mitochondria has a lot of surface area, so all these inner folds here are really folds of that inner membrane, and that's kind of been the theme for the GI system and now even nutrition, that increased surface area in this case allows for chemical reactions to happen. Each fold is sometimes called a crista, that inner membrane, those folds. And it's again these redox reactions that help to power this process. This is similar to the picture that I drew at the very beginning that shows that glucose has high energy at the very top of the staircase, whereas when the energy gets dropped off, it'll be captured largely by these energy carriers, these high energy intermediates, NADH and FADH2. And remember, these guys then can release their hydrogen atoms in that electron transport chain. So those redox reactions will create a gradient, and then that gradient will be basically utilized to make ATP. So in this question here, which step's effective if oxygen is not available? Basically anything in the mitochondria. So the mitochondria, there's phases 2, 3, and 4. In theory, glycolysis can take place without oxygen, especially in skeletal muscle, because of the regeneration of NAD+ via that enzyme called lactate dehydrogenase. And along the way, we've talked about these B complex vitamins that have played a role in helping this metabolic process. So there's that CoA enzyme from the pantothenic acid, and then the riboflavin and the niacin that will basically make or be useful in making niacin for NAD and riboflavin for FAD. So this is an older version here of 36 molecules of ATP. Anywhere in the low 30s, high 20s is probably a more accurate number, okay? When you are producing those first 4 ATPs in steps 1 through 3, it's not really using oxygen directly yet. So that kind of ATP production is sometimes called substrate level. So the production of ATP requires phosphorylation. Phosphorylation was adding the ADP with the phosphate to make the ATP. And this process, there's something called substrate level. So this is an enzymatic process. Remember, substrates are what binds to the active site of enzymes. That's going to be any ATPs that are produced in glycolysis as well as the Krebs cycle. So that'd be phases 1 and 3. There's also the other type of phosphorylation or making ATP, and it's referred to as oxidative. The oxidative level is really when oxygen plays a direct role, and that's going to be the one where you produce the most ATPs. That's going to be the electron transport chain. And oxidative phosphorylation, the reason why it's called that is oxygen is the final electron acceptor. Remember, oxygen has a super high affinity, so it'll accept those electrons. It's a nice summary diagram here showing you the different phases overall. You can kind of follow what happens to the carbons, right? 6 carbon, now you've got a 3 carbon structure, and then the CoAs, the acetyl actually has 2 carbons. That then can go to the Krebs cycle, and then here are the yields. Let's blow this up a little bit because it's pretty good. So remember, 2, 2, and 2 are produced from glycolysis. 2 ATPs, 2 NADHs, 2 pyruvic acids. The transition step, you're going to make, you're going to go from the pyruvic to the acetyl-CoA, 3 carbon to a 2 carbon molecule. And then you will make the highest number of your high energy intermediates, right? And this is really what? Is this from 1 acetyl-CoA or would it be 2? So this is from 2. This is like how I did it. It's really each acetyl goes through the Krebs cycle once, and you end up with a couple more ATPs, but this is really the big thing that you make there. And then these chemicals will release their hydrogen atoms, and this is where you make your significant ATPs in the electron transport chain. Now, when you think about glucose, glucose is a major form of energy. It is the major energy form, of course, in your blood. And we'll talk about some of these different states now. Let's talk about this process called glycogenesis. So glycogenesis, let's talk about glucose now. There's a term called glycogenesis, and that glycogenesis is going to be the production of glycogen. Remember that glycogen was this multi-branch structure here, which is really the way that we form or we store glucose. So this is the animal storage form of glucose. When does your body do glycogenesis? When you're in a fast state or when you're in a fed state? Well, when are you going to be storing glycogen? Typically during the fed state. Also sometimes referred to as the absorptive state, because that is when you are absorbing nutrients from your recent meal. So where it says there, what state is this? It's basically not California, but the state of your metabolism. Now, the flip side of this is versus, the other term is glycogenolysis. Glycogenolysis will be the breakdown of glycogen. When would you break down glycogen? And this happens sometimes if you notice, like if you have this hunger pang that you get, you're way too busy sometimes, you're doing maybe some kind of fasting, right? And you kind of ignore it for a little bit, but then you notice like maybe a half hour, 45 minutes later, you're not hungry anymore. And really during that time period, you are breaking down your reserves, and one of those reserves is glycogen, okay? So the flip of this is, flip of glycogenesis would be glycogenolysis, and glycogenolysis is taking place when you are more in the fasting state, couple 2-3 hours after a meal. So this is would be referred to as post absorptive. So that's kind of the big picture, which makes sense, right? You're going to store nutrients when you have a lot of them. Okay, it's almost like you have a big pay raise, things like that, or the state, California now, when there's an excess, the budget is doing well, you should really store or save that money, invest it, so that when the economy goes badly, you got some reserves. The same thing happens. Our body's like always freaking out to store things just in case. So after that big meal, it's going to do its best to store as much as possible, and then when needed, it will then break that down and use it to maintain your blood sugar. There's a weird one called gluconeogenesis, and this is now actually producing new glucose. So this will sometimes happen along with glycogenolysis. So the third one is gluconeogenesis. Neo is new. This is the production of new glucose, really from non-carbohydrate precursors. So what can your body use when your carbs start to go down? Fat, protein would be examples. And this is going to happen more with extended fasting. Our body only stores so much glycogen. When those stores go away, this is now when you start breaking down other things, fat, and way down the road, this is now like several weeks or at least a couple weeks of fasting where you start to then break down protein. So kind of like glycogenolysis, this will happen long-term fasting. So some of you may have heard of something called IF, which is intermittent fasting. This is this idea that you're going to do prolonged many hours of basically not having any intake other than like maybe tea or water and things like that. Several hours. Some people will do like a 16 hours of fasting, 8 hours of more normal eating, or even more extreme than that, 20 hours of not eating, 4 hours or 4 hours of then eating. So you could do whatever combination. There was a recent study that showed that there are these diabetics who are type 2 diabetics, and some of the type 2 diabetics usually don't need insulin, but long term they do need insulin. But they did some intermittent fasting studies where they fasted actually 3 days of the week. And for some of them, they stopped needing insulin and their diabetes was almost reversed, which is remarkable just from modifying your diet, reversing some of these type 2 diabetes conditions. This was a short term study. I don't know if they've been followed for several months or years, but it'll be interesting to see what happens with that. Okay. Now, the blood glucose then, how do you regulate that? What are you guys thinking? Your favorite, feedback loops. So let's talk about regulation of blood glucose. We've talked about these in lab. But basically, when you are in a fed state, typically blood glucose is high. That will stimulate the beta cells of your pancreatic islets. It's really islets. The beta cells will release insulin. And there's a couple of effects here. One is the increased expression of GLU-T transporters. And then what will we do? Glycogenesis or glycogenolysis? You want to store it, right? So that'd be called glycogenesis. And that's going to happen especially in what effectors? What effectors will do a lot of glycogenesis? That would be muscle, as well as liver. Those two things will help to decrease blood glucose. So this would be like your stim. This is your sensor control center. And then these guys would be your effectors. Also negative feedback, right? Just classic. And then the flip, decrease blood glucose. You have your alpha cells. Of your pancreatic islets. So glucose is going down, right? What's released when glucose is almost gone? Glucagon. Sounds like a commercial. So glucagon is released. That is secreted into the blood. And the big target here will be the liver. The liver can break down the glycogen. It can also do gluconeogenesis, and that will help to raise the blood glucose. So really similar, but they're having the opposite effect on the blood sugar. All right. So the state that this would happen, the second one, would be the fasting state. Okay, your fed state, fasting state. Pancreas is involved with both, but then you have two populations of cells that are going to be activated. Beta cells for insulin, alpha cells for glucagon. All right, let's change it up now. So, blood sugar, glucose, that's the primary source of energy to make ATP. But a really good source of energy as well are lipids. Your body can go into lipid breakdown mode as needed. So, everyone's like, oh, fat-free, fats are bad and things like that. Fats are very beneficial. We need them, okay? What are some roles of fats in the body? Okay, we're not talking about roles of fat on a person, but what do they actually do, okay? Triglycerides. Cell membranes. Remember, they can be modified to make phospholipids. Energy storage. Triglycerides have a bunch of calories, but they can be used for energy when needed, long term, or when somebody's fasting. Cholesterol. Cholesterol can be used to make some of the lipid hormones, so it could be a hormone precursor. Really, cholesterol can be modified to make a bile salt, and it is critical for things like blood clotting and can affect inflammation. Now, a really interesting question is, these are the things we actually just talked about. An interesting thing about cholesterol is that your liver, because it's such an important um, chemical, your liver can actually produce cholesterol, your own body's like new cholesterol if needed, via an enzyme called HMG-CoA reductase. So let's add that note there. Let's say produce new cholesterol. That can be done via the liver. And there's a specific enzyme that's called HMG. There's that CoA again, one of those B vitamins. CoA reductase. It turns out that that particular enzyme can be blocked by drugs called statins. So someone you know may have hypercholesterolemia. So hypercholesterolemia, one of the ways to treat that is to actually give them these statins. Interesting. And that will decrease production of new cholesterol, which would then decrease the person's blood cholesterol. So here are the fatty acids. Remember that they are these long chains. They come from this glycerol backbone, and there's literally like carbon, hydrogen, carbon, hydrogen, and so this is why they are calorically dense. Remember too, kind of like lipid hormones. Remember lipid hormones, they needed their own transport protein because otherwise they could clump up in the blood. It's the same thing for lipids, just normal lipids, dietary stuff in the body. They have to be transported very specifically. They're going to be using these things called lipoproteins. Lipoproteins will be the vehicle for transport. So lipoproteins, next concept here. So this is going to be the transport of lipids in the blood. There's a constant shuttling or sending off of lipids to and from the cholesterol. Some of them are from the diet. Some of them are just needed to keep the body healthy and just moving lipids from different body tissues. Lipoproteins overall are quite large. They have a fairly complex structure. They are going to be made up of these spherical structures. This is, pretend this is going all the way around. You can actually have receptors on their surface. And this part of it here that's going around, they look or should look familiar to you. These are phospholipids. But it's just a single phospholipid layer, which is interesting. There are receptors. These receptors can bind to the liver. And when they bind to the liver, they can actually get engulfed by the rigor, like by the liver. They can be phagocytosed or endocytosed by the liver. Some of these receptors are high affinity or low affinity. Oh my gosh, there's that word again, right? So remember, affinity was like attraction. So for the liver, some of these lipoproteins are very easily taken in by the liver, but some of them have a low affinity, so they may circulate for a while. Within the lipoprotein, you could also have these guys in here. Those structures there are the triglycerides. All right. And these lipoproteins can come from different sources. Sometimes I'll use the term exogenous. And what that means is that they're coming from the diet. Versus if it's endogenous, endogenous means that it's going to be produced by the liver. So there's a lot of liver activity going on, right? Carbohydrates being sent to the liver, storing or getting broken down by the liver. The liver is really the central organ when you think about metabolism. It was kind of analogous like the brain and the spinal cord being the central organs in your nervous system, but the liver is really doing, it's really the central hub for metabolism. Now, I know what you're thinking. There's got to be different types of these, and I want to know them all. That's good. All right, so these are lipoprotein types. And we'll just number them. Okay, so the first one, these are called chylomicrons. The chylomicrons are from the GI. Mucosa cells. Sorry about that. Let me clean this up. So mucosa cells. These GI mucosa cells, especially the ones from the small intestine, are called enterocytes. And these are the ones that'll actually enter into the lacteals, but then eventually they will go into blood circulation. So remember, the core of each villus is a lacteal, and then eventually all that stuff will drain into the cisterna chyli, the thoracic duct, which then allows it to go into the blood. Content-wise, in other words, what's inside of these structures, they tend to have a lot of triglycerides. So TGs are triglycerides. And their role is to deliver a lot of these fatty acids to adipocytes, so you can get some fat storage. And then also deliver some of the fatty acids to, FA is fatty acids there, to muscle cells. And that'll be for what? Potential ATP production. It's kind of interesting, right? Because these guys here, they're going to come right from your diet, and then they will actually deliver some of these guys for storage. The liver's really not involved with them. Eventually, what's left over will get picked up by the liver. So the source of these, of course, would be dietary. So would that make it exogenous or endogenous? That would be exo, from outside. This is your diet. They do have a receptor on their surface. Kind of a unique concept, but we alluded to it a little bit. It's an ApoE receptor. Turns out ApoE has high affinity, okay? If it's high affinity, will it get picked up by the liver rapidly? The answer is yes. So high affinity means that's going to be easily endocytosed by the liver. And it's sometimes called a receptor-mediated endocytosis. So this was something we described in 430 where there's receptors on some liver cells, it binds to it, and then that triggers a phagocytosis process. All right. All the other ones that we're going to list, numbers 2 through 4, are produced by the liver, so they're all going to be endogenous. So let's go to number 2. Number 2 is called a VLDL. The VLDL, that stands for very low density lipoprotein. You tend to produce more of these with a higher fat diet. And in terms of the content, these tend to have triglycerides and cholesterol. Their role will be similar to the chylomicrons in that the triglycerides can go to places like the adipose, as well as muscle tissue. The cholesterol, interestingly enough, can actually stay within this lipoprotein. It has its own receptors. Remember those APO receptors? And it turns out that there's going to be 2 of them. One of them will be ApoE, and then the other one's going to be something called ApoB100. Remember that the ApoE is the high affinity one. Turns out that ApoB100 is going to be a low affinity one. Interestingly enough, what will happen with the VLDL is that it can actually get transformed into the next one. After triglycerides are delivered, what will happen is that the ApoE receptor will fall off and not be expressed. So ApoE receptor is not expressed. What does that mean then? One thing that it means is that we're actually going to change the name of this guy. It'll be our 3rd category. So again, the liver produces this. All of these are going to be endogenous from now on, right? The liver will produce the VLDL. One of the main things that it'll do is it'll deliver triglycerides to various tissues. In that process of delivering it, the ApoE is not going to be expressed, and it's going to be left with the ApoB100. It's now going to be called an LDL. LDL stands for low density lipoprotein. Now, for these guys, they will have what receptor on its surface? Only the ApoB100 receptor. So remember, that was the low affinity receptor. Because of that, it will have a long lifespan in the blood. It can circulate for a couple days versus hours. It's going to be more difficult for the liver to endocytose these guys. So what was left in terms of their content? The triglycerides were delivered, so these guys are mainly going to have cholesterol. The LDLs are the ones that can cause damage to your blood vessels. That cholesterol can get delivered or accumulate, let's say, along the tunica intima of arteries. When that's happening, that is referred to as atherosclerosis. So what kind of cholesterol would LDL be? Would this be the good or the bad cholesterol? Exactly. So let's say, therefore, LDL is typically called bad cholesterol because it's the one that can lead to atherosclerosis. Let me back up for 1 second just to go to this chylomicron part. And remember, these guys, these chylomicrons, they will get taken up by the liver. I just wanted to make sure that we re-emphasize this. The LDLs have the ApoB100, and so they're not going to be taken up by the liver as easily. When they had that high affinity receptor, it was referred to as the VLDL, but the LDL no longer expresses that. Now, there's got to be something to the rescue, right, to basically offset the production of the LDL, and there is. The thing that you can produce to offset it is this final category that we'll talk about next. Let me get caught up with our slides here. So here, this is the general structure of the lipoprotein phospholipids. You got your aporeceptors and then a bunch of TGs in there. You can also have some cholesterol in there as well. There are enzymes that are released or produced by your tissues that can break down that cholesterol, like fats. And basically what we've been talking about are these different types of lipoproteins, the chylomicrons. We emphasized a bunch of that already. The LDL. The final category is the HDL. So the HDL, so L was low, so this is going to be the HDL, high density lipoprotein. And these densities are figured out, I believe, centrifugation. They figure out how, like, the dense ones will tend to sink more and the light ones don't sink as easily. This is, again, 2 through 4. So this is another example of endogenous. So this is produced by the liver. And it does have a receptor that is a fairly high affinity. So the receptor is sometimes called an APO1 receptor. It is a high affinity one. The role of this particular lipoprotein is actually to pick up cholesterol from peripheral tissues. So again, it's kind of like the yin and the yang, right, of LDL. One can deliver it, but this is the one that can pick it up. Because it can pick it up, therefore we're going to call this guy HDL. We'll call that one the good cholesterol. And ideally, when you're checking your patients, ideally you'd want to have a nice ratio, meaning you'd want that person to have high HDLs and low LDLs. The picture has been confused a little bit. Now they're finding that there are some subcategories of LDL, and some of them may actually be beneficial, but currently they don't fractionate or break down those subcategories. They probably will in the future, or maybe with some of these tricky patients, to actually differentiate those different types of LDL. Just when you think you have it all, right, there's some more detail. After a fatty meal, a couple hours after a meal, you can actually see chylomicrons in the plasma. Isn't that amazing? So this one here is a person who hasn't had a meal, a fatty meal recently, and then a couple hours later, you can actually see like a bubbly material in there, and those are the fats that you have enjoyed a couple hours prior. LDL, you got the ApoB100, but again, that's the low affinity receptor. And then atherosclerosis is happening in everybody, even at a small age, even at like early teen years, you can actually see evidence of atherosclerosis in a bunch of blood vessels. HDL, I focused in on the APO1 receptor, which was that high affinity receptor. And this is nice because it can just shows you a nice overall pattern here, right? LDL can potentially deposit cholesterol, and then the HDL will pick it up. So ideally, you'd want high HDL and low LDL. And just some associations, right? Why is LDL considered bad cholesterol? Because it's correlating with atherosclerosis. HDL would correlate with less atherosclerosis, okay? And some other trends here, right? If you do some bad things like smoking and obesity, HDL tends to go down. Exercise and moderate alcohol, now this is actually being debated, but exercise has not been debated. High HDL, okay? And then what about some of these other things that can happen? High fiber in your diet, that will tend to cause a decrease in LDL. High fat, an increase in LDL, but sometimes an increase in HDL, depending on the type of fat that you're having. High sugar, increase in the LDL. All right. So what happens to these fats? What happens when they are being actually used as fuel, and what happens when you take them in? So let's talk a little bit. And again, these are potentially big topics, but we got to just kind of get into like the main overall of them, right? Just the big picture. So in terms of lipid metabolism, lipids can be stored. So especially in the form of triglycerides. They can be used for energy, oxidized to make ATP, especially by muscle. And sometimes they are used for structural functions in the body. So examples as a phospholipid, as a bile salt, as a hormone. The storage tends to happen when you're in a fed state or a fasting state, right? Whenever you have excess of something, you tend to store it. And when do you have an excess? Usually when you're feeding, right? So this is especially when fed. And when you think about it, what hormone is dominating in that fed state? Insulin. Again, we backed it up with the carbohydrate aspect. High carbs after a meal, that can increase the insulin. Way more actually than this. This tends to increase it some, but not as much as carbohydrates can. But the main stimulating hormone for storing adipose is again insulin. Now, let's get into the breakdown. So that breakdown of fats is called lipolysis. This is basically fat breakdown, especially triglyceride breakdown. When does your body want to break down fats? What kind of scenarios? When your blood glucose is starting to drop? Starvation modes? Fasting modes? Some folks are doing low carb diets. Well, when you don't have a lot of carbs in your diet, that means you're not going to have a lot of glycogen that you're storing in the liver. And so that means you're going to be breaking down fats. When you do a lot of intense exercise, they say around 20-30 minutes into some cardiovascular exercise like jogging, 50% of the ATPs are actually coming from fat. And an interesting situation is diabetes. Diabetes is like you're at a buffet, but you can't eat any of the food because the insulin is not working, right? So the main sugar or the main energy source is glucose, but that can't be used. The body will then start to break down fats. All right. Now, when you think about triglycerides, you have this 3-carbon backbone and then a bunch of fatty acids that come from that, right? These are carbons here. And every little corner or angle there is a carbon. Now, what can these parts be used to make? That glycerol backbone is a 3-carbon. What was that 3-carbon molecule that was produced after glycolysis? It was pyruvate or pyruvic acid. That can get converted into acetyl, attach a CoA to that, and that can go into the Krebs cycle. This is again trying to illustrate that you can use fats as an energy source. Now, these are carbons here. The carbons can be pulled off 2 carbons at a time, and these 2 carbon subunits, again, it goes back to this acetyl-CoA. That acetyl-CoA can then again feed into the Krebs cycle. This process of removing 2 carbon subunits has a specific name. That's referred to as That is called beta oxidation. That's the removal of 2 carbon units from fatty acids. This is especially done by the liver. Remember, the liver can be a place where fats from adipose tissue can get shuttled to. As the liver is doing this, what will happen sometimes is that these 2 carbon subunits, right? The 2 carbon subunits are acetyl groups, right? Sometimes these acetyl groups will come together. Each acetyl is 2 carbons. They can sometimes compress together to form 4 carbon compounds, and they can be found in the blood. These 4 carbon compounds have an interesting name. They're sometimes called ketone bodies. Ketone bodies can also then be found in the blood, and they can be evidence that a person is breaking down lipids. And again, why would they be breaking down lipids? Right? These are some of the things that we talked about. That can be a reason why that lipids are being used as a energy source. Are there examples of these ketone bodies? Absolutely. Acetoacetic acid. Doesn't that sound like 2 acetyls put together, right? There's another one called acetone. There's a third called beta hydroxybutyric acid. So this acetone, this acetoacetic acid, sometimes can give people a fruity breath when they are producing them at high volumes. So a diabetic comes in, they're looking bad, they may be going through a crisis because their sugar is not being maintained, and they may be having something called diabetic ketoacidosis. Okay, so there's a condition called DKA. DKA is a lot of the times the way that type 1 diabetes is diagnosed in children. They're not having a good time. Maybe they're sick. They're fighting off a cold or a flu, and they're producing these ketone bodies. They're not producing enough insulin, and they come into the ER and they have DKA. So they're diabetes. They have diabetes. They're producing ketone bodies. These ketone bodies are acidic. They lower the pH, right? Acetoacetic acid. This is an acid. And so that's why their blood pH can drop as well, and that could lead to issues. And again, ketone bodies are not necessarily bad because your body is just evidence that your body is using lipids as an energy source. When you start to produce high levels of them, then it could be issues like diabetes. All right. So that is basically lipolysis, right? This is the breakdown of fats. This is a nice summary diagram just to show you that everything is getting a little bit cut off here. But right there, if I bring this down for a sec, notice how glucose, amino acids, and triglycerides, they have a common way or a common breakdown product, which is acetyl-CoA. And that can go down into the Krebs cycle. So it's just the acetyl-CoA is just kind of like this central molecule that all food groups can be turned into as an energy source. And then again, if they can accumulate as due to fat breakdown, you can get these ketone bodies. So lipolysis, 2 carbon fragments. Beta oxidation is that process of removing those 2 carbon subunits. When is it triggered? We talk about starvation, diabetes, things like that. So ketogenesis is what? Just the production of ketone bodies. Okay. So ketogenesis is when that is being produced. Again, small levels, you know, intermittent fasting, you may produce some, but then in extreme situations like diabetes, you can have really bad metabolic acidosis. All right. Now, the final fuel source potentially can be proteins. So protein metabolism. We talk about carbs as a source, lipids, and then there's proteins. This one's fairly brief because this is really, really extreme as a fuel source. Remember, proteins are made up of subunits. Those subunits are called amino acids. So when you build proteins, that's called anabolism. And what are some examples of proteins, right? They could be like antibodies, enzymes, things like that. And when will you tend to make proteins? Fed or a fast state? Again, that fed state. And what will help to stimulate that process? Again, it's insulin. So there's bodybuilders who have used, if they don't want to use steroids like testosterone, they sometimes will use insulin and growth hormone to try to build up their muscle mass. Tricky. Opposite of anabolism or synthesis is going to be catabolism. So proteins as a source of ATP. Like I showed you in the diagram, amino acids can get converted into acetyl-CoA, which then can feed into the Krebs cycle. This can be done by the liver, which makes sense, right? So the metabolism, if you're ever stuck like, oh my, what organ is doing this? It's probably the liver. Amino acids too can be converted into, may have to be, several of these to make glucose. Maintain your blood glucose. What was the name of that process to make glucose from non-carbohydrate precursors? That process right there, that's called gluconeogenesis. So glucose, neo is new, right? This is the production of new glucose that didn't exist, and amino acids can be the source of that. All right. All right, let's go here now. So amino acids can be made from other amino acids, and that's sometimes referred to as transamination, just moving that amino group. When you break down proteins, it's called deamination. We talked about that at the beginning when we highlighted the liver functions. And it turns out that there's some of these amino acids that are essential, meaning that your body can't synthesize them. And then there's some non-essential ones where you're using other amino acids to make a different amino acid, and that's going to be using that process called transamination, where you're just moving an amino group from one chemical to another to make a different amino acid. Okay, so up here, let's make a note that there are different types of amino acids. There are ones that are essential. There's about 10 of them. You have to get these from the diet. And then there's some non-essential ones. Let's make a note here. Can be produced by the liver. And the liver, to make these, is doing a process called transamination. So just think of it as transforming one amino acid into another. And again, to show you that basically everything can get converted into that acetyl-CoA. And that acetyl-CoA, of course, feeds into the Krebs cycle. Carbs, amino acids, fats, ketone bodies, it can be used for all those processes. It's kind of this pivotal or central chemical. All right. All right. So one thing that you may have noticed is that when you are in this absorptive state, you have a lot of nutrients that you've just ingested. Post-absorptive, it's been a couple hours since a meal, and the absorptive state is going to be dominated by insulin. All right, this is when you are going to store things, and insulin from the pancreas is being produced. Let's look at these crazy diagrams, but I'm going to summarize them to try to just make it a little bit easier here. So in this process here, this is showing you like basically after a meal, you're storing like crazy. Glycogen, you're storing fats, you're producing proteins. Proteins are being produced. These are not numbers we're memorizing. Those are just a little crazy, but let's summarize that. There's two major states. One of them is absorptive. The other one is called post-absorptive. After a meal, what would you like to be stimulated? You want to stimulate what? Basically synthesis. You're going to store and synthesize glycogen. You will store and synthesize triglycerides. You will store and synthesize proteins. What hormone is critical during that absorptive state? Insulin. There are these growth factors that may play a role. And then even some thyroid hormones, but focus on insulin. On the flip side, the post-absorptive state, you're going to go the other way. You will do things like glycogenolysis. You will produce ketone bodies. Remember, this is a form of lipolysis. You will even break down proteins. This is really gluconeogenesis, right? What hormones kick in for this process? The opposite of insulin, produced by alpha cells this time, glucagon. Epi can also stimulate this process. Epinephrine, that is. Cortisol, especially with prolonged fasting. Again, this just highlights how powerful insulin is. It's really the main one that's dominating. Glucagon is kind of a minor player, and because it's kind of wimpier, it can use other hormones when you start going the other way, when your blood sugar starts to go low in that post-absorptive state, all right, or that fasting state. Okie dokie. All right, final topics here. So let's talk about BMR. Person's BMR is their baseline metabolic rate, their basal metabolic rate. Basal. Baseline metabolic rate is going to be about 2,000 calories a day. And usually when you try to assess it, this is usually when somebody is basically nice and calm, okay? They're calm, fasting, overall just not agitated. So you hear about situations where you can increase your metabolism and therefore burn more calories. When you measure people's outcome in terms of weight gain or loss, you can exercise like a monster, and that's great, of course. Great for cardiovascular health. It's great for muscle tone and strength. But if you have a crummy diet, doesn't matter how much exercise you do, right? So really, it's about the intake, unfortunately. That's sad, okay? So now, how do you actually estimate BMR? The estimation of BMR, you got to go back to your overall cellular respiration equation. And that is what? C6H12O6, 6 oxygens. You want to know this overall equation. You get what? 6 waters, 6 CO2s, and then, let's do the high estimate. 36 ATPs. What are we missing? And heat. So when you think about what you can use to measure the person's metabolic rate, there's really some different options, right? You can look at things like heat production. So this is, let's say, estimating the BMR. Heat production. You can also look at oxygen use. Water, that'd be hard to estimate. CO2 production, possibly too. Modern day, for estimating a person's metabolic rate, really what's practical, because what are you going to do? Put them in like a container and then see how much the temperature changes over time. You do this with animals sometimes, it's hard to do with people. Oxygen consumption too is not very practical. So really there's a hormone again that stimulates metabolism, and that's going to be a person's thyroid hormone levels. You'll look at a hormone called T3, which is thyroxine. All right. So that's the estimation part. What are some factors that affect a person's metabolism? Let's list that. That would include things like gender. Males tend to have a higher metabolism than females because of muscle mass. Okay, again, not all males have a higher muscle mass than all females, but overall, right? It's the guys that, when you are on a date, you say, "Oh, you're gonna eat that? Yeah, okay, no, okay, all right, all right." Alertness. When someone's asleep, their metabolism is lower. Kids, especially that toddler age, oh my gosh, when you're about 3 years old, that's when your metabolism is crazy. If you have an adult try to do exactly what a 3-year-old does in terms of body movements, they won't be able to keep up. Interestingly enough, diet plays a role. Turns out that protein tends to increase a person's metabolism. Protein is hard to break down. Remember, you got to go through the hydrochloric acid and all these different proteases. So when someone's having a lot of protein, typically their metabolism does increase. Exercise, can never discount that. Up to like a 15 times increase in their metabolic rate. And that's during the activity. After the activity, you can actually stay fairly, there's like an afterburn where your metabolism is maintained for a while. Right? So if you're sloughing around, maybe you want to, use some weights a little bit there to at least get some activity going on, right? And this is, people have their phones, it's all kinds of stuff that makes us want to be like a sloth. Body temperature, 98.6. Of course, that depends on the person. There are ways that heat can be transferred from one person or from a person to their environment. Okay, so let's just talk about heat. Let's refer to this as heat loss and gain. There's overall, a handful of these mechanisms. One's conduction. That's going to be via contact. Those hot summer days, Sally, my dog, just wants to lie on the tile floor and just conduct heat to that. There's also convection, transfer of heat via some kind of fluid. Could be a gas or liquid. Right? So somebody falls into the cold Sacramento River, they don't have a life jacket, they can go to hypothermia pretty quickly because heat loss via water is very rapid. Okay, I actually just jumped in the pool a couple days ago, and that was some cool water in there. Okay, so it's like quick cool down. I'm going to skip down to evaporation. So when water evaporates from your skin, it's really the warmest water molecules that are leaving, and that will cool off your skin. So this is just basically via evaporation, sweating, and there's this evaporative cooling that takes place when you go from a liquid to a gas. All right, final topic here. By the way, your thermostat for your body temp is the hypothalamus. And let's talk about responses to a cold temperature, cold environment. What are you going to try to do in this cold environment? You're going to try to conserve heat, right? And actually even produce heat if possible. So some of the responses include peripherally, you're going to do a peripheral vasoconstriction. So that will keep the warm blood to the core. You can do some shivering, and during that shivering process, this is going to cause your skeletal muscles to contract. You will eat food, especially protein. That'll ramp up your metabolism. And then what would you do to your surface area? Surface area, you're going to want to decrease that, right? Curl up, decrease surface area. And that will basically decrease heat loss. And possibly curl up with something warmer with you. You've ever heard like a 2-dog night, right? That's like a really cold night, right? Dogs are warmer than us. And then what would happen to your hormone production? Increase in thyroxine production. And this would take several days. This is not overnight, and this is not you just like sticking your head in the refrigerator. It'd have to be several days of exposure to cold. This is a slower effect. The increased thyroxine production is going to increase your metabolism. And I have a picture here of these dogs that are used for these Alaskan races, these Iditarods. But they are basically, these small dogs are about 50 pounds each. And for them to maintain their body weight, right, because they're exercising, they're in the cold, they got to feed each dog roughly 10,000 calories a day. So if you want to extrapolate that to someone who's maybe 150 pounds, that would be, you would be having to eat 30,000 calories a day to maintain your body weight, right? That's an obscene amount of food. I think the swimmer, that famous swimmer, Michael Phelps, was eating around 10,000 calories to maintain his body weight because of his intense exercises, and his metabolism was crazy high. Amazing. All right, next. Oh, and by the way, just last year, believe it or not, they're using some banned substance to win the race. Just poor dogs. So there's the thyroid gland that's found in the mediastinum wrapping around the trachea. All right, let's finish it up with, what about the response to warm environments? It's basically going to be the opposite, right? To warm or hot environments, they would include what? Instead of peripheral vasoconstriction, peripheral vasodilation. So this is going to release heat when that happens. Instead of shivering, the person will sweat. That is evaporative cooling. What happens to your appetite on those really hot days? Actually, appetite oftentimes goes down. I remember visiting my sister-in-law in Alabama. People would just be like hanging out on the front porch, just sipping like sweet tea, okay? Because you just want to eat. Your hunger goes down. You're kind of apathetic, as well as anorexic is sometimes what it's called. Increased surface area. That's again to release heat. Notice this rabbit here with the big ears. Some of that is to actually release heat. And then there's this cute little animal called the antelope ground squirrel. These guys are found in the desert. They're one of the few mammals that you actually see active during the day in these extreme desert temperatures. And what they do is that they like dig these really deep burrows, these deep holes. And when they get hot, they run all the way down on the ground, like several feet down, and then they spread their arms and legs as far as possible, touch the ground, and then cool off. All right. Nutrition-wise, just a few thoughts on this. There's all these different nutrients as sources of food. Of course, you need micronutrients and Macronutrients. The macronutrients are the four categories, right? Lipids, carbs, proteins, and nucleic acids. All the micronutrients are the smaller quantities that you need as well, like iron and vitamin B12. I would go back and look at the functions of your fat-soluble vitamins. And again, this kind of emphasizes it. Vitamin A, night blindness. Vitamin D, calcium issues. Vitamin K, issues with clotting. Vitamin C is collagen synthesis. That's not one of the fat-soluble ones. And niacin, thiamine, let's leave that to some of your nutrition classes. Same with, I would know the roles of these guys, but I'm not going to give you the specific deficiencies. Okay, I'm going to wrap it up and take a look at Canvas if I have any announcements before the exam. Have a great day. Thank you.